This video will walk you through testing assumption 3, which is that the errors are normally distributed using SPSS. And to do this, we're going to use the measures of leverage, Dfits, and Cook's D. So here I'm looking at the data set ComNode 6. I have information about 14 communications networks, their cost, the number of ports that they have, and the amount of bandwidth that they require. So I'm going to go into Analyze, and then Regression, select Linear. My dependent variable is cost, and my independent variables are number of ports and bandwidth. Obviously, well, we would hypothesize as I increase the number of bandwidths and the amount of bandwidth and the number of ports, then my cost should most likely increase. I'm going to go into Save here, and I am going to save my standardized Dfits, my Cooks, which is Cook's D, and my leverage values. Then I'm going to click Continue and click OK. So I get my regular regression printout, and aside from these additional residual statistics, you're going, okay, well, where is the actual information? The information itself is here in this, back in the data set. So this first new column is Cook's D, the second new column is the leverage value, and the third new column is my standardized Dfit. So leverage, the first thing I want to look at is leverage values. That measures how much the current observation influences the fit of the regression model. And an observation is said to have a lot of leverage, a lot of influence, if its leverage value is greater than 2 times the quantity k plus 1, all of that divided by n, where k is the number of independent variables. So here we have 2 independent variables, number of ports and bandwidths. So 2 plus 1 is going to be 3 times 2 divided by n of 14. So an observation is going to be said to have leverage if its value here under this leverage statistic is greater than 0.428. So here it's looking like observation 1 is potentially exerting some leverage. So let's move on. So we'll keep that one in mind. Let's move on to go and look at our Dfit. Our Dfit tells us the change in the predicted value of our dependent variable, y, if the current observation were omitted. And that is going to be high if its value is greater than the square root of the quantity k plus 1, all of that divided by n, and then multiply that by 2. So here we have 2 plus 1 divided by 14. Okay, take the square root of that. It's going to be 0.46, and then multiply that by 2, and I'm going to get 0.925. So any observation with a Dfits greater than 0.925 would potentially be exerting some leverage there, and that's going to be in absolute value terms. So that means observations 1, 2, and 10 are potentially going to be issues now. And then let's go and look at Cook's D. Cook's D is a measure of how much the residuals of all cases would change if the current observation were omitted, and that's value is high roughly if it's greater than 4 divided by n, so n here is 14, so that's going to be high if it's greater than 0.28. Now that one is like the most loosey-goosey kind of estimation. You can also do Cook's D, looking at an f-test and compare it to its critical value using an f-test, and that would be a little bit more exact. So from this, I'm really going to say, the ones that appear to definitely be the highest, I've called attention now to observations 1, 2, and 10. 1 and 2 are, doing pretty poorly using Cook's D. Number 10, not so badly, and number 10 also didn't do as badly under leverage. So if I were to omit variables, I would potentially consider definitely, maybe omitting observations 1 and 2. It's one of those things where it becomes, a judgment call as to whether or not you definitely want to omit it.